Hey, this is Mr. Hanson. We're going to be looking at rectangles today and measuring some area, determining some area. And the big idea is if you're given so many lengths or slats um, of perimeter to work with, what's the maximum area that you can come up with? So I already have some rectangles drawn here. I have this 1 by 7 rectangle, and if you think about the perimeter, we'd have 7 plus 1 and double that, you get 16. But if we had a 1 for a width for our area, with a perimeter of 16 for our area, we're going to get 7 of those squares. So I'm going to mark that in here. Then we have 2 right here for a width. And so 2 plus 2 plus 6 plus 6, that's 16. We have the same perimeter to work with. And this time when our width is 2, we have 12 for an area. So our area is increasing as our width gets larger. Here our width is 3, and again the perimeter is still 16, but the area is now 15 units. So we increased just by 3 that time, and now we've got a width of 4 and a length of 4. And so the perimeter is going to be 16 again, but the area is also going to be 16 when the width is 4. And then, let's see, I forgot to draw this one here. I'm going to do you might notice the similarity. Actually, these two are congruent rectangles, but now the width is going to be 5 and the length is going to be 3. So if the width is 5, we're back down to 15. And then if the width is 6, we're down to 12, and if the width is 7, you might have guessed it, we're back down to 7, like that. So there you have it. And if we were to kind of graph what's going on, what the relationship is between width and area, you might notice at 1 we're at 7, at 2 we're at 12, maybe right about there. At 3 we're at 15. At 4 we're at, well, let's make the 3 right there, 15. At 4 we're at 16, and then we're back at 15 again. We're back at 12, back at 7, and you might can tell that it's going to increase and then decrease on a graph. And if you remember from earlier in the year, this creates what we call a quadratic function. So that's kind of what we're looking at. We're looking at how the width of a rectangle is, if the perimeter is held constant, how the width could determine the area. And we've kind of maximized it. If we wanted to find the maximum area, or the most number of squares, we'd probably want this one right here, which is a width of 4, which would give you an area of 16 there. So that's kind of the idea. Well, let's take a look at this with more of a real life word problem. When I was living in the rural West in southeastern Utah, I noticed a lot of cowboys would have a corral that had some fencing, but then one side of the fence was kind of a natural fence, kind of like a rock ledge or something. So they just needed to use 3 sides of the rectangle to corral in their cattle. And so a cowboy has 600 feet of fencing, and with that 600 feet he's got a length and a width that he has to kind of take into account. And he could do this lots of different ways. He could go very long on the length and very skinny on the width, or very large on the width and small on the length, or somewhere in between. But what he wants to do is maximize the area for his cattle. So he wants the most bang for his buck. He wants the most area on the inside here. So I'm going to write an area function. Area as a function of width equals length times width. You might remember this from 3rd or 4th grade. Length times width of a rectangle is the area. But we don't want to write it this way, because really we're asking when W is the input, what's the output going to be? So we have to write length in terms of the width. So let's let's write a whole separate equation for just a minute. The perimeter that's the amount of fence, is going to equal the width plus 2 lengths. And the perimeter happens to be 600. And we want to get length alone so that we can plug what length equals in right up there. So that's kind of the idea. We're going to do length in terms of the width. So let's subtract W from both sides. And we got 600 minus W equals 2 lengths. And then divide both sides by 2. So length equals 300 minus 0.5 W. Okay, now we're going to come up here back to the area, and we're going to write area equals, instead of length, now we're going to put that 300 minus 0.5 W. And then we times that by the width. And so there's a formula. We can plug in the width and figure out the area. That's the whole big idea there. It's a function, so it's kind of nice. And we could write it a couple of different ways. We could multiply this together. I lost my W right there. We could say 300W minus 0.5 W squared, and these mean the same exact thing, so it's whatever is easiest to use. And with a function, what we're trying to do is we're trying to kind of look for some input-output matches that are good landmarks that can kind of help give us a picture of what's going on. So that's what we're shooting for here. And some of the landmarks on our function, let's just talk about this for a minute. Some of the landmarks might be, if this is area and this is width, when the area equals 0, okay? When the area is 0, you've got some x-intercepts, so that might be important. So I want you to think about this for a minute. I'm going to rewrite this. 0 equals 300 minus 0.5 W times W. Okay, so this is when y equals 0, or the output 0. And I want you to think, okay, well, what if W was 0? What if the input was 0? We put a little 0 right there, and then a little 0 right there. And this turns into 0 right here. We get 300 times 0 is 0. So 0, 0 is kind of one of those landmark features of this graph. Now I want you to think of, what if this whole section was 0? Then that whole section times this would be 0. So I'm going to go 0 equals 300 minus 0.5 W. Add 0.5 W to both sides. And then divide by 0.5. And we get W equals 600. So here's in hundreds. Here's 100, 200, 300, 400, 500, and 600. There is another landmark feature right there. We've crossed the x-axis twice. We have 2 x-intercepts. Now once you find those 2 landmark features, you can find another landmark feature by thinking about some symmetry with the quadratic function. In the previous slide we talked about this upside down U shape, and it was symmetric. So look right here, you can tell that if we found halfway between 0 and 600, it'd be 300. So let's plug in 300, that's my x, or my W, my input, and see what I get from my output. So I'm going to go over here, I'm going to go ace of 300 equals 300 minus, let's fix that. Okay, minus 0.5 times 300 times 300. So I just plugged in 300 there and there. And so if we simplify this, half of 300 is 150. So 300 minus 150 times 300. And that's 150 times 300, which happens to be 45,000. Okay, so At 300, we're at 45,000. Let's count these in thousands. 10, 20, 30, 40, 50. So we're at 45,300 right there. So what's going to happen if we were to kind of fill in some points here? We increase quickly, then we kind of start to level off, and then that's our maximum, and then we decrease slowly, and then we kind of pick it up again like that, and there you have it. But the most important point, maybe the most important point on this whole graph, is this point right here. It's called our maximum. We want to maximize the area, so we know we want a width of 300, because that will give us a area of 45,000. Okay, so if our width is 300 right here, and so we have 600 for our total perimeter, and we have to split our length up, so we have 300 left, so half of 300, our length would be 150, and 150 there. And if we were to put this into either of these functions, the perimeter or the area function, if we put the width in for the area function, we're going to get out 45,000 when we put in 300. Or if we put in 300 for the width on the perimeter function, or on the perimeter formula, we'd find out that the length is 150. And that would maximize our area. That would give us the most room for the cows in the corral to move around. And that would help the farmer solve his problem. So thank you for listening in. I appreciate you staying in tune with my YouTube channel, and wish you tons of success on any problem similar to this or anything you're doing. Thanks again. This is Mr. Hansen signing out.